Yo, yo, yo. Welcome to Fluids. And my name is Ron, and I will be your fluids guide today. Today, we are going to continue our learning of fluids with the continuity principle. Now, the continuity principle is also known as conservation of mass. So if you've had me for a physics class, we've studied conservation of mass. If you've had me for thermodynamics, we've studied conservation of mass. I can see that I'm getting some glare on my paper. Let me see if I can fix that. Sort of fixed it. There we go. All right. I'm going to show you the continuity principle in a variety of ways. I'll start with a non-steady state. What that means is that mass can accumulate or deplete. So in non-steady state, maybe I've got this tank and I have some mass flow in, and sometime later I have some mass flow out, and I had some initial mass, and at the end I've got some final mass. Well, just like the energy balance, just like balancing your checkbook, you start with some initial mass, you bring some mass in for a certain amount of time, you let some mass go out for a certain amount of time, and when you're done, you have some final mass. Let's think of this in terms of jelly beans. Let's say that I started with 10 jelly beans. And then I had 5 jelly beans come in, 5 jelly beans per second for 20 seconds. And then I ate 10 jelly beans per second for 7 seconds. Let's see. 10 jelly beans in my jar, add 100, now I have 110 jelly beans. Eat 70. How many do I have? 40 jelly beans. Now you can replace jelly beans with slugs of water, with pounds mass of water, with kilograms of water, with any fluid or non-fluid, and that's the conservation of mass. Now you could have more than one of these coming in, so we could put a sum, more than one going out, but there it is. That's the general conservation of mass. Now, it can be made more complex by using some calculus and addressing some other issues with the mass and its movement, not necessary at this point in a one-credit competency, core competency. All right, well then, what would steady state look like? What steady state means is that there's no accumulation, no depletion. In other words, the initial mass and the final mass have to be equal. When you adjust this equation for that, well, and the times also have to be equal. So basically you get that the sum of the mass flow rates in has to equal the sum of the mass flow rates out. And if there's only one mass flow rate in and one mass flow rate out, it's equal. Steady state continuity. That's not that hard. I call it the gazintas equals the gazadas. Whatever goes in has to equal whatever goes out. Let's talk about what mass flow rate is quickly. So I've got some water and is flowing in a pipe. And let's let this pipe have a diameter of d. And let's let the fluid have a density of rho. So diameter, density. And let's take this chunk of fluid and let it have a length of L. So mass flow rate is equal to mass divided by time. And what is the mass of this chunk of fluid? Well, I would say that mass is density times the volume. I think that comes from the definition of density. And what would the volume be? Let's see. That would be the area, pi d squared over 4, or pi r squared. So area times length, right? Isn't volume of a cylinder area times length? So we'd have density times area times length over time. What's length over time? Oh yeah, velocity. So the equation for the mass flow rate of a fluid is m dot equals rho a v. And that v is really speed. We're not doing this in a vector form, but I always put the arrow over it because we have the other v of volume going on here. So m dot equals rho a v. Let's see, we said something here about mass equaling density times volume. So if we divide both sides by density, we'd have volume. So volume flow rate would equal mass flow rate divided by density. Hey, the density goes away. Volume flow rate is area times speed. The continuity equation works for volume just as it did for mass if the density is staying constant everywhere. So if density is a constant, then we can do initial volume plus the sum of the volume flow rates in times time in minus the sum of the volume flow rates out times time out equals final volume. All right, there we have it. We have the continuity principle. It's also known as the conservation of mass. One of the things in there is mass flow rate, so we spent a little bit of time defining mass flow rate, volume flow rate. That's it. We'll be applying this in class. Have a nice day.